So to round out SN2, we're going to be looking at how the quality of the nucleophile affects the rate of the reaction. And then we'll take a look at how the solvent affects the rate of an SN2. So when we talk about nucleophile quality, what we're looking at is something called nucleophilicity. This is just simply the rate a nucleophile will attack a substrate. Just because we label something as a nucleophile doesn't mean that they react at the same speed another nucleophile will react with. And so we use some descriptors like we might say some nucleophile is strong if it reacts very quickly, or it's weak if it reacts very slowly. Or you might hear me use the descriptors good versus poor to describe their reactivities. Now, just to show an example of this, if we take hydroxide and react it with methyl iodide, it reacts very quickly in an SN2 fashion. But if I use a similar nucleophile, like for example, water, and I use the same substrate, I can draw the same exact mechanism. It reacts very slowly with, water reacts very slowly with methyl iodide. And so there's a definite difference between certain nucleophiles and how they react. So you can see in this table here some common strong nucleophiles and common weak nucleophiles. Now, this is not an exhaustive list, it's just representative list. But I want to kind of point out something. You could try to memorize all of these, and if you want to do that, there's more power to you. Um, but I want you to look at some trends. What do you notice about all of the strong nucleophiles? Number one, there's the presence of a full negative charge versus, in the case of a weak nucleophile, there's only partial negative charges. So these oxygens over here are, no, not partially positive, partially negative. They don't have a full negative charge, whereas all of these nucleophiles over here have that full negative charge. Now, another factor that affects how strong or weak a nucleophile is something called polarizability. And this is the ability of an atom to distribute its electron density unevenly as a result of external influences. Now, basically, kind of a good trend to remember is that the bigger the atom is, the more polarizable it is, because those electrons in the outer shell are farther away from the nucleus. Then it's easier to influence those electrons because they're not as held captive, so to speak, by the nucleus. And one thing I want to point out here is that you'll notice that we got all the halides and the strong nucleophiles except fluorine. So, or I should say fluoride, F minus. F minus isn't on the table because it really depends on what solvent you do the reaction in. In some solvents, fluoride is a very good nucleophile. In others, it's actually a very weak nucleophile. So with that, let's kind of transition into the effect the solvent plays on an SN2 reaction. Now, in order to kind of set this stage, you need to kind of note that we categorize solvents in two kind of major categories. There's polar versus non-polar solvents. And I'm not going to go in depth on how you determine that. That's something you should know already, how to look at molecules and determine if they are polar or non-polar. But in general, polar solvents can help stabilize ions. So they can help stabilize the nucleophile, the leaving group, and the transition state. Because those polar solvents, because they're polar, they have a negative end and a positive end, partially negative, partially positive. So they can help stabilize chemical species that are also negative or positive. And so I'm going to focus kind of exclusively on polar solvents. And within polar solvents, we can further break these down into what are called protic and aprotic solvents. So we have polar protic and polar aprotic solvents. I just want to see if you can. I'm going to take a minute here or a second. And I want you to see if you can see a structural difference between them. They're all polar, but what is a noticeable difference between these solvents? In protic solvents, there is a hydrogen bonded to a highly electronegative atom. Most commonly, that's an oxygen, but it doesn't have to be. It could be a nitrogen. And protic solvents are capable of hydrogen bonding. And polar aprotic solvents, while they may be polar, they do not have a hydrogen bonded to an electronegative atom. Now, the kind of what in this case of how a solvent affects an SN2 is that SN2 reactions greatly favor aprotic solvents. I want you to look at this table down here. So in this, what this table is demonstrating is we're doing this SN2 reaction with various nucleophiles, the halides. And first thing I want you to look at is to compare the trend between protic and aprotic in terms of rate. Notice how much quicker the reaction rates are by using an aprotic solvent. So that's one very important trend that I want you to note, is that there is a drastic increase in the rate of reaction, depending on whether a protic solvent is used or an aprotic solvent is used. Now, the other trend I want you to be aware of is comparing the halides just to themselves within a column here. Look at the rate for if a protic solvent is used when you compare iodine and go to fluoride. So iodine's at the bottom of the periodic table, fluoride's at the top. And notice how the rate decreases. As you go from bottom of the periodic table to the top. So in this case, if you use a protic solvent, iodine's the fastest nucleophile. But if you switch to an aprotic solvent, now look at the rate. The rate increases as you go from iodide to fluoride. Now, fluoride is the most nucleophilic ion when you're comparing the halides. And this kind of points back to what I had mentioned on the previous page, where fluoride could be on either list of good or poor nucleophiles because it depends on the solvent that it's placed in. So there's the two trends on this table are going to be very important to know. First of all, the main trend that SN2 greatly favors aprotic solvents. And then when it comes to the halides, the order of nucleophilicity of the halides depends on whether it's done in a protic solvent or an aprotic solvent. So let's talk a little bit about why. So I kind of highlighted the what, but why does SN2 favor aprotic solvents? So aprotic solvents can only stabilize cations and not the anions, like nucleophiles. And I want you to think about that term stabilize. So remember, if something is more stable, what does that mean in terms of its energy? That means if something's stabilized, it has lower energy. So if the nucleophile, which is a reactant, which is a required part of the SN2 transition state, if the nucleophile is not stabilized, then that means it has a higher energy. Okay, let's put this into perspective with an energy diagram here. So when the reaction is done with an aprotic solvent, the reactants have a much higher energy, and therefore it requires less energy to get over that activation barrier. So it reacts much faster. So if we look at an aprotic solvent like acetone, for example, no OH bonds here. So it's not a protic, it's an aprotic solvent. And that oxygen, because it's partially negative, can only help stabilize ions like cations, which are pretty much just spectator ions in reactions like this. So um, doesn't really help in stabilizing the reactants. Now, if we take a polar protic solvent like water, for example, water can stabilize cations, but they can also stabilize anions because water is capable of hydrogen bonding. And what the stabilization process is called, it's called solvation, which is just the surrounding of an anion or a chemical species by the solvent. The more it gets surrounded, the more stable it makes that ion. And so if chloride here, let's assume chloride's kind of our nucleophile. If chloride is solvated a whole lot by water, it's stabilized. And that creates this situation here in a protic solvent. And the energy of the reactants is much less than the energy of what the reactants would be if it's done in an aprotic solvent. So let's do a little bit of practice, and then we're going to move away from SN2. So for each of these pairs of reactions, we're going to figure out which one will have the higher rate. Okay, so when you approach a problem like this, you want to note where are the differences. Okay, so if you look at our first one, let's start with the substrate. Notice the substrate here has the same leaving group, because sometimes that'll affect the rate. If you have a really good leaving group versus a really poor leaving group, the better the leaving group, the quicker the reaction is going to be. So these have the same leaving group, so that's not a difference. How about our nucleophile? Okay, well, the nucleophile here in both cases is hydroxide. So there's no difference in that. Because remember, the quality of the nucleophile affects an SN2. Okay, so SN2 you greatly favors really good nucleophiles. So the only difference here is the solvent. So if we look at the solvent here, water is protic because it's got an OH bond in it. DMSO is aprotic. Now, over time, and what I highly recommend is, spend a little bit of time memorizing the common protic and aprotic solvents. So if we go back here, I would just kind of commit all these to memory. Their names, structures, if they got acronyms, you'll want to remember those because it's going to save you a lot of time um, to in problems like this, where if you just look at a solvent and know instantly if it's protic or aprotic, it'll save you a lot of time in doing these problems. So all we're doing here is comparing the solvent, protic versus aprotic. And we know that the trend is SN2 favors aprotic solvents. So the reaction that's going to react the quickest is going to be the one with the aprotic solvent. That's the only difference between the two. Okay, so let's look at the next pair. In this pair, we have the same leaving group. And now let's go look at the nucleophile. The nucleophile here, that's a little different. Okay, the nucleophile in the top reaction is iodide. And on the bottom reaction, it's chloride. And then the solvents are the same. Now, we don't want to just glance over the fact that the solvents are the same. We want to really pay attention because we're dealing with halide nucleophiles. Halides react differently in protic versus aprotic solvents. So we look at this, we have ethanol as the solvent. Ethanol is a protic solvent. We know that because it's got an OH bond in it. So I'm going to go to my trends here. And if we look at the first column here, we can see that iodide reacts the fastest in a protic solvent versus chloride. So the top reaction will react better in a protic solvent. Now, had that been something else, maybe if the solvent was acetone, something that was aprotic, then the opposite would be true. So it's very important as we go along that you know the factors that affect the rates of these reactions. So at this point in time, we've only talked about SN2. We haven't gotten into SN1 yet. And what we're going to head into next is kind of skipping over to elimination and looking at a somewhat related elimination mechanism compared to SN2. And we'll see that on the next video.